So today we will continue chapter 8. So this chapter we start talking about the phase equilibrium. And we said phase equilibrium, this is the condition at which we have phase transition occurs for any substance. And we started talking about the criteria that we can use in order to know the conditions at which phase transition will occur. So we said if we have available data, there are some equations. Directly we can use these equations in order to calculate the vapor pressure or saturation temperature, for example. Okay, but if we don't have this available data, then we need to use mathematical models in order to find these phase transition conditions. Okay, and there are some criteria that we need to use this criteria in order to define the phase transition conditions or phase equilibrium conditions. The first one we discussed was entropy. We can use entropy as one of the criteria to to find phase equilibrium conditions, but the limitation with using entropy is that we need to calculate the total entropy change. And total entropy change is summation of entropy of the system, entropy of the surrounding, and sometimes it's difficult to calculate entropy of the surrounding. Okay, so this is why we need to use another criterion. The second criterion we start to think of is Gibbs-free energy. And we said we have molar Gibbs-free energy, and we ended up the previous lecture with this remark. So we said at phase change or at phase transition, there is no change in the molar Gibbs-free energy. And again, molar Gibbs-free energy, not Gibbs-free energy. And the difference, as we discussed in chapter 1, we have like extensive properties, intensive properties. Gibbs-free energy itself is an extensive property. Molar Gibbs-free energy is intensive property. So Gibbs-free energy itself is not constant during phase change conditions, but molar Gibbs-free energy, the intensive property of Gibbs-free energy, this is the one that is constant during phase change conditions. So molar Gibbs-free energy for the first phase, molar Gibbs-free energy for the second phase at phase equilibrium conditions, they are the same. And we compared between entropy and Gibbs-free energy. So we said for any process to occur spontaneously, that we have total entropy will increase, molar Gibbs-free energy for the system, not the surrounding, only for the system, will decrease. And if you have two different cases, any substance will go from the case with higher molar Gibbs-free energy to the case of lower Gibbs-free energy. And again, all of these things only can be applied for pure substances. Okay, because when we start dealing with mixtures, then we faced another issue that molar Gibbs-free energy are not constant. And this is why we start to think about different criteria to describe phase conditions or phase equilibrium. Okay, so the first thing, we started with entropy. We have limitation with entropy because in order to calculate entropy or consider entropy as criteria, we need to calculate entropy of the surrounding. And sometimes this is not possible to calculate. Then we used Gibbs-free energy. Gibbs-free energy was good, it can be used for pure substances. There are two limitations of Gibbs-free energy that enable us to continue using it as criterion for phase equilibrium. The first one is whatever they applied for pure substances cannot be applied for mixtures. So this is why when we study Thermo 2 next semester or next semesters, then you will see that we are not using molar Gibbs-free energy as phase equilibrium criterion for mixtures. So this is one of the limitations of using molar Gibbs-free energy. It can be used for pure substances, but not for mixtures. There is another limitation we will discuss right now, but this is the first one. One of the other things that makes us think of using different criteria, we have something called chemical potential. Chemical potential, one of the things that we can use as criterion also for phase equilibrium. And chemical potential, it's something related to the molar Gibbs-free energy. And actually for pure substances, they are equal. Okay, so chemical potential, molar Gibbs-free energy, they are the same, only for pure substances. For mixtures, they are different. So this is why, again, Thermodynamics 2, you will calculate molar Gibbs-free energy, you will calculate chemical potential, and you will see different values for both of them for the system that you have. But here in this course, we are focusing on pure substances, and in pure substances, they are the same. There is no difference between molar Gibbs-free energy between chemical potential. Okay, the chemical potential, this is defined as the partial derivative of Gibbs-free energy with respect to the number of moles. So as we said, Gibbs-free energy itself, this is extensive property But when we calculate it with respect to the number of moles, then we are converting it from extensive to intensive property. So chemical potential is not equal to Gibbs free energy. Chemical potential equal molar Gibbs free energy. Chemical potential equal the intensive property, which is Gibbs free energy. So this is the equation of calculating chemical potential. So chemical potential is the derivative of Gibbs free energy with respect to a number of moles. And what is Gibbs free energy? Gibbs free energy is molar Gibbs free energy times number of moles. So this one is equal to this Gibbs free energy. Here we have derivative of two variables. Okay, do you remember chapter 6? If you have derivative of two variables, so it will be first variable times derivative of second one plus second variable times derivative of first one. So first variable times derivative of molar Gibbs free energy plus molar Gibbs free energy times derivative of the second variable. And again, recall the basic laws of calculus we explained in chapter 1. dNi by dNi, this is equivalent to 1. Clear? For phase change conditions, for pure substances, phase change occur at fixed pressure, at fixed temperature. Water, phase change of water occurs at 1 atmosphere, 100 degrees Celsius. Only one pressure, one temperature value. So this will be 0 for pure components. So if this is 0, then we can end up with chemical potential is equivalent to molar Gibbs free energy. And again, this is only valid for pure substances. So when we start to define criterion for phase equilibrium for pure substances, again, we started with entropy, we have limitation with entropy. Then we decided to go with molar Gibbs free energy or chemical potential. They are the same for pure substances, not for mixtures. Okay. So molar Gibbs free energy, chemical potential can be used as criterion for phase equilibrium for pure components. But if we move to mixtures, this molar Gibbs free energy cannot be used. Okay, and again, there is another limitation of molar Gibbs free energy. We will discuss it after we solve the example today. So how we can use this one? All what we said, how we can know or how we can use this criterion to know phase equilibrium condition. So let's assume if I give you this table. This table represents molar Gibbs free energy data at different pressures and at fixed temperature. So all of this table, like at given temperature. So at this given temperature at 0.8175 bar, I will calculate molar Gibbs free energy. 0.8176 bar, I will calculate molar Gibbs free energy. 0.81, calculate molar Gibbs free energy. How you can calculate this criterion in order to know your phase equilibrium conditions. So let's see here what we have. Here we have molar Gibbs free energy for the liquid phase. This column describes molar Gibbs free energy for the vapor phase. So at this given temperature, at 0.8175 bar, this is the value of molar Gibbs free energy for liquid, molar Gibbs free energy for vapor. These values are not equal. So this means this temperature, this pressure, at these conditions, phase equilibrium does not exist. Okay, we don't have phase change will happen at this given temperature, at this pressure. Let's try at this given temperature at 0.82 bar, for example. So molar Gibbs free energy for liquid is this value. Molar Gibbs free energy for vapor is this value, and they are not equal. So here, if you have molar Gibbs free energy for two phases are not equal, this means these conditions does not represent phase equilibrium conditions. But if we see this one right now, at 0.8176 bar at the given temperature, this is the molar Gibbs free energy for the liquid. This is the molar Gibbs free energy for the vapor. These values are almost what? Are equal. So when you calculate molar Gibbs free energy at given temperature at 0.8176 bar for liquid or for vapor, molar Gibbs free energy was almost the same. So this means phase change will occur at given temperature and at this pressure value. So this is the key here. So this is how we are using this criterion. So we always use this criterion to know the conditions at which phase equilibrium or phase transition will occur by calculating the value of this criterion by molar Gibbs free energy or chemical potential, or as we will discuss next lecture, the fugacity, for example. Compare the value of this criterion for the first phase, compare the value of this criterion for the second phase. If you have the same value of this criterion for different phases, so this means this pressure and this temperature conditions are the conditions at which phase equilibrium exists, or are the conditions at which phase change will occur.